Hi, my name is Michele Meo. I'm from Politecnico di Torino. And in this talk, I will present our contributions as Politecnico di Torino to the project 6GTWINS. So our key contributions consist in some tools to be incorporated into network management that interact with the digital twin of the network. So in particular, we have two kind of contributions: machine learning-based prediction of network conditions and some stochastic models of the access limits. So I will now try to provide some additional details on these two contributions. Let us start from machine learning-based predictions of network conditions. So here, the objective is to focus on real-time communications that are implemented through RTP at the transport layer. So we take some of these applications for video conferences or voice over IP or gaming. They would carry their traffic through RTP. These applications, they have experienced a very fast growth in popularity and then also in the amount of traffic they are carrying. And for this reason, they are the more and more important for the network. So the quality of these applications is usually measured in terms of quality of experience, which becomes particularly critical considering that they are real-time applications. And the quality of experience depends very strongly on network conditions, on indicators like latency and losses. So it becomes important to predict network conditions in real time so that possibly some action can be taken whenever network conditions start to degenerate, to deteriorate, so that you can improve quality of experience or keep quality of experience high. So the objective here is, in this context, in this framework, to propose some techniques for real-time prediction of network conditions. So let me show you our approach. Assume that you have your applications going on with time, generating packets. We would define some time means and collect statistics on these packets. Statistics about the amount of packets that are generated, the time between packets, the size of packets, the presence of losses within the time mean, and so on. So, for example, this means that within this time mean, we can measure the inter-arrival time between packets, and then we can take the mean of this value as well as some higher order statistics of the inter-arrival time, and we would do the same with other indicators. So we have all these statistics, and then we would use these statistics, looking then in the recent past, trying to use the characteristics of these statistics in the recent past to predict the network condition in the near future. So let me show you an example considering packet losses. So these are two behavior of the standard deviation of the inter-arrival time. A statistic taken from the time bins of 500 milliseconds that was previously shown. And the graph on the left shows a case in which there will be a loss at this point. It is indicated by this red cross. And the one here on the right shows a case where there will be no loss. You clearly see that there is a different pattern in the two cases. So by understanding these patterns, we can assume that by monitoring this recent past, we can predict whether there would be some loss in the near future, in the next time being. So basically, we use the statistics in the last 10 time bins, which means the last 5 seconds, to predict the possible occurrence of some losses in the next time being, the next 500 milliseconds. So what we have done is, based on this concept, we have tried and tested several different machine learning tools, and we have engineered them so as to try and predict losses. So in particular, in the results that are shown here, we have trained our machine learning tools considering more than 2 million time bins taken from more than 66 hours of video calls collected from our research group. So the statistics correspond to 110 different features, which is that they are coming from different kind of statistics over different indicators. And they are collected from two different popular video conference applications. So we have tested, as I mentioned, several different machine learning tools. They are listed here. I don't want here to report details on them. Just wanted to give you an idea about the possible performance that we get. So this class 0 corresponds to the case in which in the next time bin there is no losses. Class 1, which is the most difficult to predict with fewer occurrences, it's a case in which there will be losses. So as you can see from the values that are reported here, while predicting the fact that there will be no losses is relatively easy, more difficult it is, of course, to predict the presence of losses. So we can get values of recall that in some cases are high, sometimes they are lower, but say that the performance are still acceptable. We have also tested, so this first part of the results refers to classification tools, where the classification task is distinguishing between the no loss case in the next time bin from the occurrence of some losses. We have also considered some anomaly detection techniques, but they perform relatively poorly for the prediction of losses. So while the results are encouraging, because the task of predicting losses is difficult, they clearly need some engineering. So we have done quite some effort in trying to engineer our models, and we have in particular implemented a solution for feature augmentation, but also tuning the definition of what it is a lossy beam. And what you can see from this graph is that these are the typical performance that we can get with a performance over the class 1, which is this one, which can be as close as almost 80% with, zero dot in some cases. In some other tools, it's slightly lower. So still, the fine-tuning and the engineering of the model is very important in this case. In addition to that, what we have also done, it is to consider the different kind of anomalous patterns. So we have tuned our models also for some particular behavior, like we have considered normal losses, which is what you see over here, but also the occurrence of unexpected behavior that correspond to there are no losses, but the payload type in the RTP flows changes, or the case in which there are no losses, but the numbering of packets changes corresponding to a different frame in due to the video frame segmentation. So we have been investigating how different applications actually engineer the use of RTP for their purposes. And this is reflected also in engineering our machine learning tools to have better performance. And so what we have observed is that these engineering tools can actually improve all the performance of the different machine learning tools that we have been considering. So the second kind of contribution consists in stochastic models of the access links. So in this case, we change both the scenario, so we look into the access links as well as the methodological tools we are using. We move from machine learning tools to stochastic models. So assume that we have an access link like the radio access link. And in nowadays networks, what we have is that in an access link, we have the coexistence of several different services that have different KPIs, but also different paradigms for the use of the resources, and different admission control strategies can be used to allocate resources to the different families of services. At the same time, we can also have access links where a lot of users share their resources. So the complexity of this scenario calls for some models which can, in a relatively simple way, represent the key behavior of the access link, so that this behavior can be incorporated in the digital twin. And then what if analysis, they are enabled. So having this in mind, we have proposed the stochastic models to be incorporated into the digital twins that try to represent in an accurate way these kind of scenarios. So in particular, we have been looking into access links where we have the coexistence of streaming services and elastic services. So streaming services are services which are rigid in the amount of bandwidth they require. So assume that we have the access link with a total capacity C. Whenever we allocate resources to a new instance of the streaming service, we allocate an amount of resources which is a bit correspond to bitrate R. So when we have N streaming services which are active and connections of this sort, we would use an amount NR of the capacity. So these services that typically correspond to real-time services, they would have a duration which is independent of the network conditions. And also, depending on the kind of streaming services, say, for example, video or audio services, the amount of R of resources which is allocated would change. Now, elastic services, they use a completely different paradigm. They basically use what it is unused by the streaming services, which are rigid in the amount of resources that they need, and they would share what it is left by, in terms of bandwidth, by streaming services. They would share this resource by the number of active elastic services. So, for example, here, this yellow part corresponds to the bandwidth which is left unused by streaming services. And if there is only one elastic service, it will use all of this bandwidth. If at some point, like here, we have two elastic services sharing this resource, each of them would get half of it in a fair share. So basically, the way in which elastic services use the resources is different. And the duration of the service would depend indeed on how much bandwidth they would receive. So in our model, we would consider, as I mentioned, the fact that the channel capacity is shared among connections that are allocated either according to the paradigm of streaming services or the paradigm of elastic services. On top of that, we can incorporate in our model also some admission control. The model is a stochastic model, and it is relatively easy to be incorporated into the digital twin. So the model is interesting because it allowed us to also investigate and analyze some particular behavior of the condition of the channel. Let me show you what I have in mind. First, we have been observing some complex interactions among services, even when they are of the same category, like streaming services, but they require different amount of bandwidth. So in this case, we have streaming services of two classes: audio services, which require a small amount of bandwidth, and video services, which instead require a much higher amount of bandwidth. So the red line here, whose values should be read on the y-axis on the left, correspond to the blocking probability for audio services requiring little amount of bandwidth, while the blue line refers to the blocking probability of video services. And on the x-axis, we have the load, so the number of service requests per second. So we observe this very curious and particular oscillating behavior for the blocking probability of audio services. And these are actually the complex interactions that occur among different services, which are rigid in the amount of bandwidth they use, but they require different values of bandwidth in absolute terms. So the oscillating behavior is actually deriving from the fact that when you increase a little bit the audio service, the amount of requests of the audio service, the effect of the audio service on the video service is that it becomes more or less blocking. So even by increasing only a little bit the request rate of the audio services, you would have a higher blocking over the video services. And by slightly changing the blocking on the video services, you induce the oscillating behavior on the residual bandwidth that the audio services can use. So this shows how these models can actually be effectively used to represent complex interactions among services. So these oscillations appears among services of the same kind, like streaming services, but then also as a consequence on elastic services. So for example, here we represent the blocking probability on the left for audio services, the red line, and for elastic services, which is the light blue line here. You see again the oscillating behavior. The oscillating behavior of the elastic service is of the elastic service connections is due to the fact that the residual bandwidth, the residual capacity, which is this darker blue line, whose value you can read here on the right, this residual capacity experience some oscillations. So the oscillations that we could observe on the performance for the streaming services reflect also on the elastic services. Even if elastic services can adapt, they are not rigid, and they can adapt to the residual bandwidth. So this again actually confirms the fact that the interaction among different services, they are complex. Okay, so just to show what it is happening on video services, which are those requesting most of the bandwidth, you can see in this picture here, in this smaller graph here. So then as a conclusion, just summarizing, digital twins of the network, they need models for easily creating what-if scenarios and for predicting the performance so that you can represent the action that you would put in place to react to the changing network conditions, either in real time or at steady state. So having this in mind, we have proposed tools that follow two different approaches that are complementary in their objectives, but also in their nature. On the one side, we have proposed machine learning-based tools for real-time prediction, so for prediction of the network condition in real time. On the other side, we have also proposed stochastic models for representing in a compact and effective way the steady-state behavior of the network and the interaction among different services. So this is the list of publications that contributed to the project. And then these are some additional KPIs. So a presentation on one of the two activities I was proposing, as well as the organization of an industrial panel. So this is all on my side. Thank you for your attention.